Hello, everyone. Welcome to the fourth presentation of the seminars from the Master in Quantum Computing Technology from Universidad Politécnica de Madrid. In this talk, Shervin, which is a former student of this program, will provide us a gentle introduction to quantum natural language processing. So Shervin has been studying natural language processing for some time now. He studied in the University of Paris, and he's currently working in the field of text-to-speech. And he joined this program last year with the objective of seeing how quantum computing could be applied to natural language processing. And after discovering this application, this quantum natural language processing, he decided to work on this field. And after the knowledge that he obtained, he's now providing us this overview of the field and the prospects that it holds. So with that, thank you again, Shervin, for your effort on joining us today to deliver this talk. So all yours. Thank you.
Okay. Hi, everyone. Thanks a lot for coming, and thanks UPM and Rafael for inviting me in this presentation. In this presentation, I want to discuss, so as Rafael said, the work I have done mainly for my master thesis at UPM. And I have called this thesis a gentle introduction to quantum natural language processing, because I wanted my work to be understandable both by the quantum practitioner as well as the natural language processing engineer, so people from both backgrounds. And in this presentation, I will go over this work. I have reviewed in this work what quantum natural language processing is and a few applications of quantum natural language processing. And for one of them, I have embedded my own original experiment. So yes, I hope that at the end of this presentation, you have a clearer idea of what quantum natural language processing is, what it can achieve for natural language processing, and also what are the limitations. Again, a special thanks to Gianni and Zenaida, who supervised my thesis and helped me work this, make all this work. So I will start with this historical background about natural language processing. Natural language processing is important from the very beginning of the computer's birth. Turing is considered the father of computing, and he theorized from the very start of the computers something called the Turing test, which is a test to say if a device is intelligent, and this involves the understanding of language. So from the very beginning of computers, intelligence is somehow linked to understanding of language. And I just wanted to put that symbolically, but the most important part of this historical background is that most of the changes in computing, in the algorithms, were motivated with hardware changes. So this is true mostly for the shift between rule-based natural language processing to statistical natural language processing. So rule-based natural language processing are algorithms which are made by specialists, which write rules, which are applied on computers, and those rules define the algorithm. Whereas statistical natural language processing is a trend which is more modern and that use database, which relies on data sets to create somehow its own rules to make it simpler. So this shift is mostly motivated first by the increase of computational power and also by the rise of internet, which makes a huge amount of data sets available. This is also true later when the rise of the GPUs lead to the possibility of using neural networks and deep learning, which wasn't possible before. And this is the current trend in natural language processing. And this is also based on a hardware revolution. So this is also a very historical claim for maybe studying quantum natural language processing, because there is a new device available in the near future, which is quantum computers. And this might lead to the need and the wish to explore quantum algorithms for natural language processing. So I would like to start with this question, which might be very important and abstract for someone with no background on natural language processing, which is, what is a word meaning and how does a computer encode the word meaning? So word meaning can have at least 3 different ways of understanding them. There is the cognitive word meaning, which is just what we do as human beings, and we link objects to their word and their abstract representation. That is the most, that is the most obvious signification of word meaning. And then there's the linguistic one, which we could see as lexical word meaning, and which we can understand as the meaning that we would find in a dictionary. It's all the features that are associated to a word. Is it the category, the part of speech category? Is it a verb or a noun? Is it masculine or feminine, singular, plural, and all those distinctions which kind of approximate the meaning that we have in a cognitive sense. The third way that we can define word meaning, and is the one which is used in natural language processing, is the distributional meaning. Distributional meaning is a formalism that we use to represent the meaning of words, which is based on the distributional hypothesis. Distributional hypothesis claims that words that have the same meaning will appear in the same context. They will appear around similar words. So we don't focus so much on what composes the meaning of the word, but instead of comparing words to each other, we say, okay, those words have the same meaning because they have the same context of appearance. We generally, in applications of natural language processing, we choose a basis of words. We choose words which will correspond to the basis of the vector space. And for all the other words, we count the frequency in which they appear to those basis words. And that puts these words into a vectorial space. And the main interest of having words into a vectorial space is that we can do vectorial operations on those words. And those vectorial operations have lexical meaning. So for instance, the orthogonality is mapped to the opposition in lexical opposition. So words which have opposite meaning will be orthogonal. We can also map distances into the vector space to distances of the meaning of the words. So this is the current way that we deal with word meaning in natural language processing. Another important linguistic feature that we want to discuss before entering into quantum natural language processing is syntactic structure. A sentence is generally not just words in a linear organization. There is an underlying structure, which is the syntactic structure, which connects word into dependence. This, to be very simple, I will just explain through this example. The man saw the cat on the mountain with a telescope. This sentence could be understood in different ways, depending on if we think that the telescope is on the mountain, if we think that the telescope is the object that the cat has, or if we think that the telescope is the object with which the man is looking at the cat. So these three meanings rely on the structure of the syntax of the sentence, depending on if we want to connect telescope to each of those words. So there is a tree structure underlying every sentence. Lambeck has proposed, which is a linguist, has proposed a way of formalizing syntax and parsing, which parsing means knowing all those dependencies, which relies on pre-group algebra. So this is basically a way of calculating if a sentence has a valid structure. Each word has an atomic group being determinant, noun, adjectives, and those inverts. They invert to the left or to the right. And a sentence is only valid if they all cancel out. So there are some examples on the bottom. The man saw the cat on the mountain with a telescope. If we consider that with a telescope is the way that the man sees the cat, this all cancels out because the inverts here, noun cancels, here noun and noun cancel also, and then adverbs cancel out here, and there is only the special symbol S that is left. So the syntactic structure is the way to combine words inside the sentence. And this is very important to define the sentence meaning and we will see it just in a moment, because the main problem is we can't use the same distributional hypothesis for sentences because there's too many sentences. That's the reason we never see a dictionary of sentences, because words are atoms and we can all define them, but sentences are built through composing these words. And we can always come with an infinity of them, and there is not enough context words or context sentences, and each sentence basically appears only once. This is why we have to come with a new way of representing the sentence meaning. And this is what the DisCoCat framework aims towards. So DisCoCat stands for distributional as the distributional hypothesis, compositional as the composition of those words into the syntactic structure, and category. Category is a field of mathematics that maps objects which are connected in a similar way to another structure. So in this case, syntax, which is connection, are mapped into quantum circuits, as we will see later. Okay, so as we just discussed, distributional hypothesis and compositional structure leads to defining a data structure that can encode the meaning of sentences. This is done through generally through an algorithm which is the CSC algorithm, and this uses tensor products to tensor the vectors for each word of the sentence, using the syntactic structure to decide how to build those tensorial products. So using these steps, we can build a tensorial representation of the sentence, which output is a superposition representing the sentence meaning. Okay, so now I would like to discuss use cases for this DisCoCat's modelization. We will see three of them. First is sentence similarity. As we just discussed before, having vectorial representation of words, the first very obvious use case is to measure distance between such objects. And we can do the same with sentences. We have sentences and we want to know how far the meaning of first sentence is from the second sentence. So O'Riordan has done work on hybrid classical quantum workflow to do this. There is an algorithm to do quantum nearest neighbor. This is the algorithm nearest neighbor. We find in a data set of sentence, we find the nearest sentence of a sentence that we target. But the problem is the CSC algorithm that we just discussed before leads to an overhead which defeats the purpose of the speed of the quantum nearest neighbor. So there is no way, unfortunately, at least without quantum RAM to do this, and quantum RAM is not available. So this is why there has been studies done to find a workflow classical quantum. The main ideas are there on this slide. The sentences are mapped to bit strings. This is done using a mapping for every basis words, and then we map sentences with the words that they correspond to. For instance, if we have basis word man and we want to analyze a sentence which is John, we will probably say, okay, John corresponds to the basis word man, and then like stand and walking would be combined together to form a new verb, maybe like run. So I'm just making up examples, but the idea is to combine the basis words and their representation into bit strings to come up with bit string representations of sentences. The data sets, the whole data set of sentences we want to find the nearest neighbor for is encoded into a superposition of those bit strings, and that's where quantum comes on the scene. And the target sentence is also encoded as superposition of bit string. And then to find the nearest neighbor, we do amplitude measurements. We encode them into the amplitudes, and then we do the amplitude tomography, which are the measurements, and those show the distance to the base sentences. So here there is an example in this histogram in which we are trying to find the closest the closest neighbor to the sentence adults stand inside. And to the other sentence, children move inside. So all those sentences here are bit strings, and they encode the sentence adults sit inside, adults sleep inside, and all those. And we can see because the measurements are probabilistic, it's not always the same result. We repeat the measurement a certain amount of times, and we take the maximum of those. So that's how we finally find the maximum, the sentence which is the closest. Okay, we'll go to the use case 2, which is which is the first one, which was actually implemented on a quantum computer. And this use case is question answering in this case, but what it really is binary classification. So as we've seen with the CSC algorithm and the DisCoCat framework, we can represent sentences into dependencies, and we can use category theory to map those sentences into quantum circuits. This is generally done with hyperparameter gates because, what's really important in category theory is the number of inputs and outputs of each elements. In the case of linguistics, each element is a word, and it has a number of dependencies which represent the inputs and outputs. In the case of quantum computing, there are quantum gates in those quantum circuits. So some of those quantum circuits have to be parametrized, and this is noticeably true for the rotation gates. And this parametrization can be done with regard to a certain task like question answering and to a certain database, a data set. So in this case, a set of questions with true false answers. So we can train in a very classical way we can train a model to learn the actual parameters of those gates in order to represent the data sets and the task. So that's what has been done with optimization techniques and classical optimization techniques. I just want to show this diagram. Note that it's not a standard representation of quantum circuits, but it's a very close to the representations we are used to. And we actually map sentences here. Here is the sentence, Alice, who loves Bob, is rich. So it's Alice, and who is there and has a connection to Alice, rich, and to Bob, because it's a word which connects those three words within the sentence. Here is the verb, loves, which takes as a subject who, and takes as an object Bob here. So this is this is the experiment I have focused most in my thesis, because I wanted to reproduce those results, and that's what I did with data that we made ourselves. I also wanted to have those data both hand labeled and also, because that was what was done in the original experiments I had seen. The labels were not hand labeled, but done with a certain set of parameters, and then they trained the device to find those parameters from scratch. So I wanted the hand labels because that was more of a real life usage. And what I noted is that for each extra parameter, so each time the sentence grows, the total fitting score was reducing, and that was problematic. But there is other works that have been done that assess this problem by basically increasing the size of the quantum circuit. So that's a good news for the fitting properties of the model, but that's also bad news, because increasing quantum circuits is not a very easy thing to do currently because of the limitations we have for the technology. We don't want quantum circuits to grow too big. So that's what was done in those in reproducing those results. But we also tried something new as to the original experiments, was to add to add logical connectors. So we wanted to implement logical connectors to those sentences. All the sentences were subject, object, and subject, verb, object, and we wanted to add the possibility to connect sentences with logical connectors. So very quickly, why do we want to use logical connectors and why it's so important, in my opinion? It's because they have predictable truth values for question answering. That's very important. So if we want consistent data set as an input, it's very easy to extend that data set with logical connectors, keeping the consistentness of the truth values of all the sentences with logical operations that we know how to process. So that was we used the and, not, and or operations we can see in their diagrams with the Lambeck framework, like the Lambeck background, linguistic background, that they all have two input outputs. So we use the just the basic circuits with two outputs in order to represent the logical connectors as well as the intransitive verbs. And we had, so yeah, that's a sentence connecting dogs chase cats and don't purr. So that was the examples that we had in our data set. And what we saw is, what we expected firstly is that adding more logical connectors would reduce the fitting properties, as we said, increasing the number of parameters decreases the fitting properties. But we did obtain some relatively good results, so 70%, 62% later. Sorry. So now I want to go to the last use case, which is representing hyperonymy and entailment. So first, what is hyperonymy and entailment? They are other linguistic concepts. Hyperonymy relation is the relation of supertype and subtype. So in the reign of animal, it's very easy to see that. We say that, so cats are, felines, and felines are mammals, and mammals are animals. So this is the hyperonymy relation. On the other hand, the other concept that we will need to understand this is the entailment relation, which can be seen like it's kind of the same relation, but for sentences. So when we say the cat was killed, it entails that the cat is dead, which is more general, and which entails that the animal is dead, which is even more general. We can represent, using the DisCoCat model, these in relationships into the data structure that we're using. And this has been done by Martha Lewis, using pure states and mixed states instead of only pure states. Up until now, we have used only pure states, which means that all the sequence of qubits were deterministics, whereas we can encode them into a probabilistic mixture. And in this case, what has been done by Martha Lewis is representing the hyponyms, which are the more general, the less general objects, into the pure state, and represents mixed states as the sum over its hyponyms. So in the case of feline, for instance, the mixed state for feline would be the sum of the pure states for cat, tiger, jaguar, etc. So we can build their density matrix this way. And if we do multiple measurements, we can infer the density matrix of a state. And when we order the density matrix, this is equivalent to having the hyperonymy relation. So that is a way of having a data structure that represents hyperonymy through ordering their density matrices that we can infer through measurement. So when we use this extended framework in the quantum circuits that we've seen earlier, the output of circuits will be a sentence, as we've said earlier, and this means that we can encode the entailment, which is the equivalent of hyperonymy relation for sentences, and we can have this algorithm to predict entailment of sentences. Martha-Lewis also provides a way of representing negation in this case. So that's also very handy. And I think it's work which is very much worth mentioning. And yes, we can see here the results. The last lines are the so yes, it was used using a data set which basically has two sentences and say if they are entailed or not. And the three first models up there are the supervised classical approaches, and the models that follow are the model using those operators, density matrix and positive operators. So we can see that, yeah, it's pretty accurate, and it can, yeah, it's. So yes, time for conclusions. The main quantum advantage for quantum natural language processing is the possible increased interpretability compared to neural network. This is the case mainly because the quantum circuit remotely translates the original sentence through the syntax. So we kind of understand what is happening under the hood and why the operation leads to the binary classification result in the case that we've seen. The main limitations are, well, the same as all the quantum field, near intermediate scale quantum computers, which means that there is a lot of possible errors. Another limitation that we tackle during the question answering problem is the universality and scalability that we have seen has been assessed, but at the price of increasing the quantum circuit size. And that is a problem in the NISQ limitations. And another limitation is the coverage for logic. We have discussed a couple of possibilities, but moreover for conversational logic, because in the daily conversation, logic operators are not so formal as mathematical logical operators. For instance, if I say Tom is not rich, that doesn't mean that he is poor. And this is what someone would expect applying only mathematical logic. So yes, I believe I'm at the end of my presentation. I hope you enjoyed it and have a clearer idea of what quantum natural language processing is, what quantum computers have to offer for natural language processing. I'm more than happy to try to answer any questions that you have.
Thank you, Shervin. Thank you very much. So if anyone has any questions, please feel free to unmute yourself or just drop them in the chat and we will try to forward them. In the meantime, I'm going to share the link for all of the seminars that we are having this week so that you can check them. This is the last one of today, but you can check the ones for the Karim, yeah, of course, feel free to open the microphone. So you can check the following talks and register in any of them. So Karim, you had a question, I believe.
Yes, can you hear me?
Yeah, but very.
What about now?
Yeah, that's better.
Okay, thank you. And thanks a lot for this great talk. Actually, it was very motivating, at least for me. I'm asking about the possibility of, let's say that I have a data set, like a sentiment analysis data set, okay? And I would like to convert all the sentences into some quantum circuits. And after that, use those quantum circuits as like the initialization and then apply some variational, QNN, for example. And after that, I do like a simple classification to do like a basic sentiment analysis. Is that possible using DisCoCat? Is that possible or not?
Yes, I think that's mainly the idea. The idea is having a data structure using quantum computers that can be, yes, post-processed as you were suggesting. Yes, I think it's very much, everything is kind of proof of works and still needing a lot of approval, theoretical and experimental, but it sounds like that's the general idea, yes.
Okay, thank you. Thank you so much.
So I see there's some questions in the chat. First, I can maybe answer Adrian's one. How is the syntactic structure of different languages managed? So yes, that's kind of more of a linguistic question. Yeah, the syntactic structure is very dependent to the language. Every language has different syntactic rules. Basically, syntactic rules are always applied to different categories. So generally, classically noun, verbs, and yes, depending on different languages, there may be more specific rules. So most of the work that have been done in quantum natural language processing has been done on English. I can also imagine some difficulties if we apply to different languages. But basically, the model is quite abstract. The Lambeck's model is just dependencies, connections between words. So that applies kind of for every syntactic rules, so that's the hypothesis is that it underlies every language, but then there will be some specificities. For instance, the using of cases in German, just on top of my head, it probably will lead to some specific implementation, maybe. That would be very interesting. Then there's Joydeep's question: what is the classical equivalent for DisCoCat CSC algorithm? Or is it explicitly for quantum realm? So no, there is a possibility to do compositional algorithms on classical computers. I think there is also, interestingly, a regain of interest for those algorithms coming from quantum natural language processing, because we try to apply those on quantum computers, but quantum computers, for now at least, are limited resources, whereas using classical computers is we have so many resources and we can apply them online and on distributed resources. So there is room for compositional algorithms on classical computers. There is an exponential speedup theoretically on quantum computers, at least without without optimizing those algorithms. So there is a lot of work on trying to optimize the classical algorithms to have this working on classical computers. So I wouldn't be able to say there is one algorithm, but I hope I can find this later. Maybe put it under the comments of the YouTube video, because there is some neural networks which are based on compositional frameworks. There's another question from Felipe. Looking at the example you have provided with the hyperonymy relation, is it theoretically possible to implement sort of a dictionary encyclopedia training the algorithm? So yes, that's kind of the problem of that algorithm. The last one for hyperonymy is that it relies on implementing these hyperonymy from resources that we have outside. So there is currently no algorithm just to go through the whole data set and have all those hyperonymy. We need to rely actually on a dictionary. So it's kind of the other way around. We need the dictionary or the encyclopedia to build this hyperonymy structure for those algorithms.
I see that Joydeep was about to ask something else. Feel free to let us know. And there's a question from Jose Carlos. Oh, there it is. There's a question from Jose Carlos on whether we are going to yeah, these recordings will be accessible through YouTube, probably at the beginning of next week, once we process everything and upload it. And there's a question from JD. So how the word meanings are stored in DisCoCat? Are they fixed or they can change based on the text structure? I mean, in a same sentence, meaning of a same word may mean different. Yeah.
Oh yeah, no. So yeah, each word has a fixed representation, which is the distributional one we've seen. So each word has a vector basically in the vector space, and the meaning is the meaning that varies on the text structure is the sentences meaning using the compositional structure of the syntax.
Okay. I don't know if there are any other questions from the audience.
Oh, I just the neural networks I was mentioning earlier, which use classical compositional, are RT so recursive neural tensor networks. So if you're looking to classical framework to do compositional compositional computing, you can neural network. Natural language processing, this could be the way.
If there are no other questions, I think we can close the session. In any case, once we upload everything, as Shervin was suggesting before, you can always reach out through YouTube or through email directly to us, and we will try to forward any questions that you have and try to make it that possible. So with that, we are right on time, so that was perfect. Thank you very much, Shervin, again for your effort and sharing everything with us. It was a great talk. So with that, thank you again, everyone, for joining as well. And we will be closing the session now. And we hope to see you again in tomorrow's session and see you there. Thank you, everyone. Have a nice day.
Bye.